All right. Well, it is 2 o'clock Central Daylight Time, so we're going to get going here. For those of you that don't know me, my name is Logan Zeck. I'm part of the engineering department here at the Allen Block corporate office in just outside of Minneapolis, Minnesota. Today we're going to be talking about best practices, chapters 8 and 11, that focuses on tall wall consideration and seismic considerations. So this is part of a series we've put together over the past few months or so that are focusing on our best practices manual. So maybe some of you guys have attended the earlier sessions. Um, well, I'll cover what we went over at the last one in particular, and at the end we'll talk about what the next one is in case any of you guys are interested. But we're really trying to cover everything, at least the main points as far as best practices go. So if you guys have any questions along the way, you're free to input them as a few already have. Otherwise, at the end, I'm going to field questions as well. Sometimes it's hard to watch for those while we're going through the presentation. But I guess we'll go ahead and jump in here. And if anyone has any issues seeing or hearing, just let me know with the question as well. So I'm going to start off just giving you a basic overview of best practices for those that haven't attended any of these yet. So best practices has really been, it's an initiative that's been around for a little over 5 years that Allen Block has been a major part of. And the goal of best practices is to move the segmental retaining wall industry more towards being designed towards walls being designed correctly, with the ultimate goal of having zero wall failures. It's a tough goal to reach, but we're well on the way here. And the implementation of our best practices manual, along with the NCMA, who have also created their own manual after we did, we're getting much closer to that goal. So following a set of well laid out guidelines not only avoids failures, but it also minimizes delays in design and construction phases. So having a set of rules like this, it benefits you in a lot of ways. And when all parameters are known and construction methods are consistent, if these methods are followed, then it's going to make everything run more smoothly. And it educates designers and installers on not only materials but also proper practices and eliminates the potential for oversights. So while it is a great set of guidelines to follow, ultimately every site that you're going to work on is going to be unique in its own ways. So it's up to you guys, mostly the engineer of record, to use your best judgment and account for actual site conditions and provide a safe and efficient design. As the years go on, we expect best practices to continue to evolve as it has since the beginning, and only improve design and construction and minimize those failures. I guess I'll go back here and just briefly talk about these pictures. I'm not going to go into the projects themselves, but obviously these are some wall failures. The top one's kind of a famous one of Allen Block, that they used construction fence instead of geogrid, so obviously they weren't following best practices there. And the bottom one I can't really speak to, I'm not sure, but it looks to be holding up that truck pretty well, so those are some interesting photos. Limitations to best practices. Obviously, I mentioned you guys have to use your best judgment, so that it's not just a set of rules that is all-encompassing. So last presentation focused on Chapter 7 of Best Practices, which was focusing on GeoGrid. So that one was a little atypical. Typically, it's one of our employees here at the Allen Block corporate office that lead those. Chad Julius in our office was involved in that one and did some of the presenting, but it was primarily led by Mike Bernardi, who's with StrataGrid. And he reviewed how grid is made and tested. He also covered what goes into the National Transportation Product Evaluation Report, and also how GeoGrid is used to build taller structures. That kind of ties into our topic this week, which is focusing on tall walls, or I should say this month, since these are monthly, I believe. He also covered proper grid placement behind the wall, and that includes unique scenarios, or I guess not unique, but all scenarios, which would include corners and curves as well, and how that was handled. We'll talk a little bit more about that as well with tall walls. And then finally covered industry recommendations for the type of grid that's being used, and also the testing requirements that are involved. So getting into today's topic, or at least the first of the two topics, is the tall walls. We'll talk about the definition. So it's not finite in numbers, but typically tall walls are going to be anything over 10 feet. You would consider a tall wall. Why I say it's not a definite number is because if there are no real surcharges or slopes above or below the wall, a 10 or 12-foot wall or a 3 or 4-meter wall, you might not have to consider as a tall wall. You might be able to design it just as you would any reinforced wall that was slightly shorter. But if you did have surcharges involved and that sort of thing, that's kind of the cutoff, is about 10 feet. So that's, again, comes back to your best engineering judgment, whether you think some of these considerations that we're going to talk about should be incorporated into a wall that's kind of in that gray area there. So, as I mentioned, several factors are going to, play into whether we consider it a tall wall or not. But if it is a tall wall, we want to change the design in a few ways, such as increasing the wall rock depth, enhancing structural fill, and maybe running a global analysis or global analyses several points throughout the wall. And we're going to talk about each of those items today. All right, so really one of the big ones in a tall wall application, one of the big major changes that we want to consider and that we often see happening and are glad to see that happening is increasing the wall rock thickness or even putting a variable wall rock thickness in. So our rules and what's incorporated into our software, AB Walls, is that if you have a wall from 10 to 20 feet, that wall rock column, the bottom half of it is going to increase from our standard 12 inches to 24 inches, and then for the top 10 feet, it would be, or sorry, for the top half of the wall, it would be the typical 12 inches. And just so you guys know, if you didn't know already, the standard wall application, it's just the wall rock is going to fill the block cores and 12 inches behind the entire height of the wall. And so that's why it's really only tall walls you see this variable amount typically. If you get beyond that 20 foot in height, or 6 meters approximately, then we still recommend the bottom half be increased actually now to 36 inches, and then we divide up the top half into 25% and 25% at 24 and 12 inches. Again, these are our recommendations. This is what's incorporated into AB walls, but you could change that variable, the different heights, to whatever I guess you chose, and you can also change those in AB walls if you guys are using it. I guess I'll plug it now because I'm going to be talking about AB walls a lot, but if any of you guys aren't using AB walls or don't have AB walls, definitely reach out afterwards. It's a great tool, and you'll see some of the outputs and that sort of thing for designing these walls. So I'm going to be sending an email within the next 24 hours, probably 24 hours, and you guys can always respond, and I'll send that over to you. Along with the tall walls having variable rock thicknesses, we also want to consider increasing that rock thickness even more at outside corners and curves. So on the right there, you can see we've got a cutout of one of our standard details for an outside curve, and we've increased the wall rock depth. And in both of these scenarios, it's done to achieve proper consolidation and compaction behind the block. So that's very important. So I didn't mention it in the last slide, but wall rock, it's called wall rock for a reason. It used to be called drain rock because it does act as a drain behind the retaining wall, but it's not intended to be used for a drain. So what we saw after a few years of calling it drain rock is that some people would take all of their site water and try and funnel it to the back of their retaining wall, assuming that it was going to drain down through the bottom and they'd be okay. But really, that's not the intention of it. It's really intended for compaction, and so that's why in these scenarios we're increasing it even further behind the wall for more proper compaction behind the wall on taller walls. And so that's why we change the terminology across the industry, actually, not just Allen block, and it's referred to as wall rock. Walls can easily fail because of down drag forces that the grid experience when there is excessive settlement behind a wall. And so on this next slide here, you'll see I have an image. This has some other things going on here. You can see that drain pipe is involved as well. But this is part of a case study that we did on a project that had a major failure. But I like this image because it shows you that they did have quite a bit of settlement, like I mentioned, because they didn't have proper compaction, possibly not enough wall rock as well. And one of the issues that causes, not just caused by the settlement itself, but you'll notice it creates sort of a bathtub effect at the top. So if you have heavy rainfall or a lot of water in that area, it'll begin to pool, and that's going to seep, cause some pressure behind the wall on its own. Along with that, it's going to increase the forces lower in the wall, can cause some bulging like you see in the wall, eventually some grid rupture. So if you don't have proper compaction, it's often going to lead to wall failures. Um, and even if it doesn't fail immediately, it's just no one wants to see the inconsistent settlement behind the wall, or really any settlement at all if we can avoid it. So I mentioned we want to increase the wall rock usage. I put that a few points in this slide because that's really one of the major changes with the tall wall application. And again, the engineer, you guys, have to carefully review the site geometry and structures above and below the wall to create a plan for how to use that space the most effectively and design this wall structure so that we're not going to see any failures like that. Along with that, inspection is very important. So down at the bottom here, you've got a list of some of the things that need to be considered for inspection as well. Confirmation of the foundation soils. So if you guys don't know, foundation soils we refer to as anything beneath the wall, basically. So not including that small base beneath the wall. So we want to make sure that we know about what's in those foundation soils. We accurately represent their parameters. Also, the retained soils, if you don't know, is what we refer to anything behind the reinforced mass. So if you have a geogrid reinforced wall, it would be everything beyond that geogrid. And then also imported materials and then reinforcement materials. So imported materials might only refer to the wall rock that we were talking about in that wall rock column, but it could also refer to the entire infill zone. If you were replacing that entire infill zone with a select fill, this is more common in fill applications because otherwise you do have to excavate quite a bit. But the and you have to put that dirt somewhere else if you're going to get rid of what soil is already on site. But if you do have a poor clay or something, or if you just need a better material for drainage or a higher friction angle to resist the loads, then sometimes what they'll do is replace that entire infill or reinforced mass with a select fill of some kind, whether that be wall rock or not. And in that case, we want to make sure that the parameters are accurate for that as well. Verifying the block. If you're getting an alum block, it should be pretty consistent across all of our manufacturers. They usually meet well above requirements as far as compression strength and that sort of thing. So you're probably getting a good block, but you do want to make sure that nothing was damaged during shipping. There's no cracks or breaks or anything that's inconsistent with the block that's going to cause any issues. And then soil placement and compaction. Again, that's compaction. It should be highlighted. That's the biggest thing here with our taller wall applications, and just make sure that they are placed as your design is listed, whether that be a wall rock column, infill mass that's imported. Everything needs to be placed as it was designed during installation. So how this compaction is done typically is with a standard Proctor test. You guys probably mostly have heard of these. And the Proctor tests look for 95% to a 98% standard Proctor to minimize settlement, ensure there's proper compaction. A lot of commercial jobs, particularly on the West Coast, will instead use a modified Proctor. So those are Proctor apparatuses in that image on the right, if you haven't seen them before, and they function very similarly. It's basically a hammer that's lifted up and dropped through that tube to compact the soil. A standard Proctor is, I believe, 5.5 pounds, and you run 3 lifts of soil within that container, and then a modified Proctor is about double that. I think it's 10 pounds, and you run 5 lifts of soil. So it's just a bit... it's kind of a more modern version of the standard Proctor as parameters changed over time, or requirements, I should say. Along with the compaction and the soil parameters, we also really want to consider water. So one of our previous best practices presentations, actually the last one I gave, was on water management. And water management is absolutely key because water is the number one enemy of retaining walls, and it can oftentimes lead to failures if it's not directed correctly around the retaining walls. And so in the bottom right there, you can kind of see a basic overview, top-down plan view of how this water should be directed on site. It should be up to the engineer to design the site so that water is handled in that regard, whether that be with swales above the wall or just grading the site so that the water doesn't make it to the wall. And on the left there, you can see a couple images. There's a swale in one of them, and there's sort of a berm in the other one, which might handle some of the the water at grade pretty well, but along with that, the water behind the retaining wall, because it's undoubtedly going to get in, at least some water, needs to be designed to be routed out. And so these aren't the best images because they don't show any drain pipes, but that's typically done with a toe drain and a heel drain, the toe drain being just beneath or just behind the bottom block, and then the heel drain being at the back of the reinforced mass towards the bottom. And there are some scenarios where these might be a little bit higher. For instance, if there were a alternate drain, which we call it, you might have those drains moved up to above grade because you don't have anywhere to exit them at the face. And if that were the case, you put a low permeability material beneath there, so that the water sort of benches off at those drain pipes. And I should add an image in here for those of you that haven't seen that. But if anyone's curious about our alternate drain, you can definitely reach out to me after I follow up with you tomorrow. So if water is not properly controlled, this goes for all walls, but tall walls it's even more of a consideration. I would say it can cause a lot of pressure towards the bottom of the wall, and you can see that it's actually 1.5 to twice the typical pressure if water is seeping into that wall and not being handled correctly. That can cause a number of different types of failure, and you can see some bulging occurring here. In addition to the compaction, they require the engineer to evaluate the overall stability of the soil structure and subsoils beneath the wall. So that could be done through a number of different analyses. You can run a global analysis. You can run internal compound stability, which we're going to talk about, as well as typical internal and external calculations. So the lower portion of the wall is going to experience higher pressures, which makes sense because there's more soil above it. And AB walls, you can see there's an output on the left there for AB walls. And I'm going to talk about that in a second. But basically, the highest pressure is going to be from the bottom of the wall to actually about 1/3 of the way up the walls where that highest pressure is occurring. And to sort of mitigate that, you can increase grid length, you can increase grid spacing towards the bottom, and you can see this output from AB walls has done that. There's one single core spacing at the bottom of the wall where 2-core spacing continues through the rest of the wall height. I'll talk about it a little bit more later, but just so you know, 2-core spacing is what's standard for GeoGrid in the industry right now. But there are scenarios like this, particularly in tall walls, where you'll see single core spacing, maybe just at the bottom of the wall, maybe for a good portion of the wall as well. And I guess I should also point out that the coloring is different here. It may be hard for you to see, but these bottom geogrid layers are orange because in AB walls we represent different types of grids with different colors. And so that would be a stronger geogrid towards the bottom of the wall, whereas which was just commonly seen in a tall wall, whereas there was a lower strength grid towards the rest of the height. So I mentioned global analyses as well. Global analysis isn't something that AB walls can do for you, but a global analysis is always recommended for a tall wall application. In a shorter wall, a more simple wall that's not going to have a lot of surcharges or slopes above or below, sometimes it's avoidable running a global analysis, especially if you're running in AB walls and you don't get the warning. We have a warning if your slip arcs are far behind the wall that you may want to consider global. If you don't get that, you may be able to avoid it. However, it's always a good idea to run this, especially if there's anything on the site, particularly poor soils that lead to a concern of that. But a tall wall application, like I said, we always recommend running that. And what it's basically going to tell you most often is you're going to need to increase your geogrid lengths, at least towards the bottom of your wall. Sometimes increase the spacing towards the bottom, just like we saw on that last screen, or else increase your buried block amount. Because what we're really trying to do with a global analysis, I should say, is interrupt those slip arcs, the worst case slip arcs that run beneath the wall. And so particularly important when we have a tall wall with a lot of soil and a lot of pressure up above. So internal compound stability, if you guys don't know, it's been incorporated into our software for quite some time. ICS is how it's abbreviated, but basically what it is, it's a modified Bishop's analysis. It's similar to a global analysis, but instead of running slip arcs beneath the wall like that last image you saw, it runs slip arcs from above the wall envelope down through each block course of the wall. And it doesn't replace a global analysis by any means, but like I mentioned, it may be all that's required on simple, smaller walls. Sometimes you don't have to consider global stability as much. But we recommend running both because ICS is a more complex, more in-depth internal calculation than your standard internal and external safety factors are going to give you. And that warning I mentioned in our software, AB walls, occurs when more than half of the slip arcs are further than the wall envelope, so further than typically twice the wall height back. If those slip arcs are really pushed pretty far back there, that tells us the worst case ones are probably even further back and they probably run underneath the wall. So this is kind of just a graphic showing how ICS is run. It actually takes points from the back of the reinforced mass, the back of the geogrid, and then it extends them back through the slope or the grade up above, and like I mentioned, runs through the wall itself instead of beneath the wall. Another thing, it comes up less often, but it's good for you to know. All of our best practices, all of our recommendations are based off of a wall block that is at least 10 inches in depth. So you shouldn't have to worry about this if you're using Allen block because our standard blocks are 12 inches in depth, so everything would apply there. But some of the smaller blocks are sometimes 9 or 10 inches in depth. But there are other competitors that have other systems that are certainly smaller. And we don't recommend using any of our calculations and considerations if you're going to be using a block that's smaller than that, because that was the kind of the cutoff that has been considered in a lot of the analyses, not only from Allen Block but across the industry. So just keep that number in mind. It's 10 inches. And then next, kind of the second portion of this presentation is talking about seismic activity. And seismic activity should be important for anyone to consider that's in a high seismic zone, whether it be for a tall wall or a short wall. Sort of our rule of thumb is if a wall is under 6 feet in height, oftentimes we don't necessarily run seismic analyses, but that's really up to you again. If it's a high seismic zone, if you're near maybe in California near a fault line, you may even want to run that on a smaller wall. It may not be the most efficient design, but certainly with a tall wall, you're always going to want to consider seismic activity. So you should check with your local, code requirements through your local municipalities or also your state requirements. We actually use AASHTO code for whenever we run our seismic analyses, and we have, we know that those parameters pretty well, and we know how to incorporate them into our software. And I'll show you later on how you do incorporate a seismic load into AB walls. But just make sure that you're running the correct code and you know how to find the correct values. So one thing that we found is that in seismic applications, geogrid placement is particularly important. So the maximum allowed is 16 inches. If you think about that, we have an 8-inch tall block, so 16 inches would be 2 courses. And I did mention 2-course spacing is standard for all walls across the industry. Sometimes in a standard application, we do allow 3-course spacing. We never recommend going above that. But if seismic activity is involved, we kind of set the cutoff there at 2 courses or 16 inches. The top layers of geogrid should also be extended in this scenario. You'll find that in this scenario, as well as some others, if you use AB walls to design your walls, it will automatically do that for you. But the length that would be typically 90% or more of the wall height for those top geogrid layers to satisfy the safety factor requirements. Also, what's going to help you out a lot in a seismic wall like this is to use a select or structural backfill for that infill mass, like I mentioned before, or the reinforced mass, which will reduce the effects of the dynamic loading. So Allen Block, what's kind of cool or unique about us is that we have done seismic testing on our product. Actually, none of our competitors in the SRW industry have done full-scale seismic testing like we have. It was done back in 2002 in Japan, actually, conducted by Columbia University and the National Research Institute of Japan. So I'm going to show you that here. This is some of the apparatuses they used. So it was after the Kobe earthquake occurred. This kind of brought up the conversation. This was well before our best practices initiative and manuals were created, but it was one of the earlier on thoughts that ended up leading to best practices is incorporating seismic into our designs. And after that earthquake occurred, we decided to replicate the forces that were involved there. And run these tests. So they were conducted on 3 wall structures. They were 2.8 meters high with a 0.2 meter base, so about 9 feet tall and a little under a foot of the base. And then there were 2 seismic tests per structure at different loading amounts. So 6 tests overall. Oh, my mouse is going away. Sorry about that. Should load up here in just a second. And so the 2 tests that were run were at 0.4 G and 0.8 G. Oh, hopefully it'll load back up here. But that's the force of gravity. So 0.4 or 40% the force of gravity is actually standard for, or it's about the highest value you're going to see for seismic loads in the U.S. at least, and most areas. You don't really get above that. Near a fault line, that's typically what we see, and so that's why that test was run at that amount. I don't know why my slides are slow here. There we go. So the first test was run at 40% the force of gravity, like I mentioned, and then the second test was set at 80% the force of gravity. So actually double what we're going to find oftentimes. And I think what's going on is my slides were set on the automatic, and that's why they were jumping ahead here. But you can see these are, when the test did occur, I think the left one there is maybe the 80% the force of gravity, and the right one is the 40%. And you can see on the lower right one, most of the damage to the soil, most of the movement was seen at the back of the geogrid mass, because the blocks are towards the bottom of your screen right there. So that's actually the back of the geogrid. And then with the higher seismic activity, you can see it sort of ruptured the entire top of the soil layer there. All right, and what we found for settlement was 60 to 90 millimeters, or about 2.4 to 3.5 inches for the 40%, or I guess for the tests themselves when they were run at 3-core spacing. But when we reduced it to 2-core spacing, we found 10 to 40 millimeters, or 0.4 to 1.6 inches of settlement. So that was a significant difference in settlement just by minimizing that geogrid spacing. And this was actually a big turning point in the industry and helped a lot with moving forward to 2-core spacing across the entire industry. It's not only for seismic walls, it's actually pretty standard for all walls now. But I'm going to show you the video here of the testing that was done. Right now, it's like I said, this was done in 2002, so it's a little older video, not the best camera, but we're looking at a top-down view of the wall right now. So the wall's towards the top of the page, and you can see the deflections that were taking place from this 40% of the force of gravity. And then this is from the front, obviously. There was a rack set up in front of it because they thought for sure it was going to fail. It actually didn't fail in any of the tests. However, it was nice that they had that there because they were able to put sensors then on that rack to measure the movement that was occurring. So not a lot of movement there, but you'll find in the next few portions of the video, we're going to see quite a bit more movement with the 0.8 G. All right, and so this is where we switch over to the higher seismic activity. This would be more. This would be a very extreme earthquake occurring right here. One thing that benefits these walls, in not only seismic movement, but any sort of movement, could be frost heave, that sort of thing, is that they are flexible. Obviously, other types of walls, such as a cast-in-place wall, would probably see some significant cracking and might crumble altogether in this sort of event. But since the blocks are able to flex and move with ground movement, it allows the wall to stand strong. So quite a bit more movement we can see here. And just after this, I'll just show you what kind of happened with the rupture at the top of the wall, and then we'll cut this one short and keep moving along here just for time's sake. All right, there you can see some of the soil being pulled apart. I believe that's right at the back of the geogrid. And you can see some cracking as well towards the wall itself. All right, we're going to jump ahead now. So here's a better image of that apparatus that was used. Again, it's a pretty tall wall. It's about 9 feet tall there. All right, and along with that, when you're considering seismic activity, it's even more important or crucial, I guess, to run these seismic analyses if you're going to have a slope above the wall as well. We found that when seismic activity combined with a slope above, it's going to make wall designs very inefficient. You'll see really long geogrid lengths or really tight spacing, and it's not very cost effective if you're going to design it that way and construct it that way. And so what we recommend actually, if you do have a slope above the wall in a seismic area, is to minimize that slope by either increasing the height of the wall so you can grade that a little flatter, or to just regrade the area if it's possible behind where that wall is going to go. It's going to help you out a lot. It's going to make the design a lot more economical. Also, additional geogrid layers are used in the slope itself. We always recommend, if you have a steep slope or if you have a slope that's in a seismic area, to reinforce that slope by placing them periodically throughout the slope. So our standard methodology that's used in AB walls and actually across most of the industry is the Mononobe Akabe or Okebi. I don't know how to pronounce it. Anyways, that seismic methodology, and it actually limits the steepness allowed above the wall in our software AB walls. And it's not the only methodology that's incorporated into AB walls. It is the primary one. But if you do have seismic turned on and you have a steep slope, you might get a warning that you would want to run a trial wedge instead, a trial wedge method. And I'll talk about that in a little while here when we talk about AB walls. So the alternate approach here, I guess I'll briefly go over it. It's like I mentioned, is the trial wedge, and basically how it works is it takes wedges of soil and it counts up the mass of each wedge and uses the slip plane at the back of that wedge and finds exactly what would be required basically for your reinforcement to make that wall to work. The problem with that is that in AB walls, no matter what your design is, it's going to make it work. If you have a 1-to-1 slope above and this is a 30-foot tall wall and there's a 0.4 G force, it's still going to find something that'll work. It might be a 100-foot geogrid, but it's going to give you an answer. And that's not always going to be a good thing necessarily. You don't want to design a wall that way. That's why I talked about how if we can regrade that slope above or eliminate it altogether, it's going to help us out quite a bit. And so be careful if you are using AB walls to design a trial wedge wall, because if the wall doesn't seem efficient at all, you might want to consider changing some of the site conditions. All right, so now I'll talk about it in AB walls like I mentioned. So I just ran a simple analysis of a tall wall. This is a 24-foot tall wall roughly. And this first image I'm just showing you, I didn't add any loads or anything to this wall, but I wanted to show you that it automatically incorporated those extended wall rock depths. So you can see, like I mentioned earlier, it extended that wall rock to 36 inches at the lower half of the wall and then 24 and 12 inches towards the top. And so that's another great thing about using our software is you don't have to consider doing these things by hand, and it's easy to forget simple considerations like these. And then we also can incorporate our seismic. So that's done using a peak ground acceleration value. You can see I input a 0.4 for the wall this time. Again, that's typically the higher end of the values that we see. Along with that, you can put in allowable lateral deflection. These are both values that can sometimes be found in your soils report, not always. Otherwise, you can find them online. There are plenty of websites. Again, we use AASHTO code, but you just want to make sure that whatever local code is what you're using to find those values. And in the wall image here, you can see that now that I've input that seismic coefficient, it's automatically extended our top geogrid layers. Again, that's typically going to be 90% of the wall height. But AB Walls is going to do that for you. Another thing to point out here, I think I was running this one with pretty poor soils, but you can see our base size was increased pretty significantly actually from that 6 inches by 24 inches. Now it's a very large base. That may or may not be necessary, but you'll see that happen if you have seismic turned on and you're running poor soils. And if you, it is a good thing to increase the base size in a lot of applications. This might be a little excessive, so if you ever see that happen and you can't change your parameters to seem to get it to go away, you can always reach out to us and talk to us about that to see if we think it is actually that large of a concern, because typically soils that are poor like clay are going to have cohesion and that sort of thing, which would eliminate that large base. This next calculation I ran, I left the 0.4G seismic load in there, but I also added a slope up above the wall. And you can see that it still extended our top layers of geogrid, but I think it actually extended all of the layers quite a bit more than we had before, and it changed to single course spacing at the base of the wall. And so again, that's something where it would be pretty hard to know exactly what the most efficient way to do this would be without running through an advanced software like this. But you can see that it's about 6 layers, I think, down there that it went to single course spacing. And one thing I should point out is occasionally you'll run across a cross section where it only changes maybe the bottom 2 or 3 layers to single core spacing. I would recommend, even though it's a bit conservative, to increase the bottom few more are single core spacing as well. Because anytime you have extended geogrid or tighter spacing or something like that on a wall design, if it's only in one small spot, it's hard for the contractor to see. It's easy for construction errors to occur. But if someone saw this cross section, it's pretty apparent that it's different at the bottom of the wall than the rest of the wall. I did have a question earlier I missed. What kind of select backfills can reduce the effects of dynamic loading? And so that's really, you're looking for something with a higher friction angle. Again, for drainage, you would want to stick to a lower fines, like our wall rock recommends less than 10% fines, but that's going to be a gravel material primarily. Could have some sand in there as well. What we're trying to avoid are those cohesive soils such as clays and silts. So really, typically it's going to be your gravel spectrum. All right, so I mentioned before how AB Walls has this incorporated to use the Mononobia-Akabe equation typically, but if you do put in a seismic coefficient and then you have a steep slope above your wall, you're going to get this warning that says, hey, if you want to run Mononobia-Akabe, we can do that, but we're going to reduce your slope to the highest possible slope to make the design work, and so you're limited there. But if you want to keep the slope exactly how it is, you don't think you can change your site conditions, you have the option to run trial wedge calculations instead, and it's going to make the design work. But again, if it's really inefficient, you're seeing some extreme grid lengths and spacings, you might want to consider changing some things as far as the slope above or increasing the wall height. So if you ever run into that in one of your designs and you're in a seismic area, definitely reach out to us if you don't know the best way to do it. Our engineering department is always here to help. If you guys ever design really tall walls, so when I say really tall, more than 30 feet in height or more than 10 meters, the standard AB Walls software will actually not allow you to run those cross sections. We block it behind another password. So you guys, some of you have received an engineering password to allow you to do up to this 30 feet in height. But if you ever want to go beyond that, you have to ask us for the password. So if you're comfortable in the software and you've designed some walls, chances are you just have to reach out to us and ask us, and we'll send that over to you. And you should only have to input it one time, but you will get that warning. Okay, so in review, we talked about tall walls, first of all, and what is considered a tall wall. Again, 10 feet is kind of that soft cutoff. Sometimes a 12-foot wall or a 13-foot wall might not have typical tall wall considerations, but 10-foot wall with a lot of other factors involved, such as slopes and surcharges, is kind of the cutoff for a tall wall. We talked about how they require additional wall rock thickness and compaction, and how that was one of the major differences and one of the most important considerations in a tall wall. Also, how global stability analyses and internal compound stability analyses are always recommended on tall wall applications. And really across the board, these are just going to help you out with any wall application, but they're not always necessary on some of the small, simple walls. In high seismic areas, or really in any seismic areas with a tall wall application, you should consider a seismic analysis as well. And in AB walls, I didn't really show it perfectly earlier, but if you do run a seismic coefficient in there, if you put a peak ground acceleration value into the software, it's not only going to give you that seismic output, but it will still give you the static outputs as well. And so it runs both, which is nice to have. And you'll notice that once you start to get to those higher seismic values, it's always going to control. So that's why we always want to make sure we're considering it. And then lastly, we talked about the slopes above the seismic grid walls and how they require additional consideration. So kind of to wrap things up, I'm going to follow up with you guys, like I mentioned, within 48 hours since tomorrow's Friday. I'm sure I will sometime tomorrow. I'm going to send you an email. A lot of you guys might be here looking for continuing education credits. I will send you an evaluation form. You just have to fill that out, answer a couple questions, and we'll give you an hour of continuing education credits as soon as you send that back. Also, next month we're going to be running over the next best practices chapters, which are 9 and 10, which focus on global stability consideration for segmental retaining walls, which we briefly got into today. And that's going to be led by a colleague of mine, Laura Horseman. That's on the 22nd of August. So keep an eye out for the invite to that. I'll also include the invitation for the times in my follow-up email. And then lastly, keep an eye out for our technical newsletter. We send these out quarterly, so if you guys haven't been receiving these and you would like to, just let me know as well after I follow up, and we'll make sure you're on the list. But they're a great way to keep in the loop with the way the industry is moving, and the next one is scheduled to go out on September 18th. So at this point, I'm going to open it up to questions. We went through that relatively quickly, so if you guys have any questions, we have some time here, definitely. Ask away. Otherwise, if you think of any later, you can always respond to my email again. When can you make this presentation available to attendees? So this presentation will go onto YouTube hopefully by tomorrow. And so we have a busy week, like I mentioned, with training here. Ideally, I'll send that follow-up email tomorrow, and we'll include the YouTube link as well. But if not, I'll send that link out separately next week sometime. And one thing that came up in our earlier presentation today, if any of you guys are interested in previous best practices modules that you weren't able to attend, just let me know in the follow-up, and I can send you the links to those videos as well. Does the heel drain convey water from the reinforced soil zone? Yes, so we don't talk too much about drainage in this particular module, but the heel drain is at the back of the reinforced zone, like you mentioned, and it's just a way to capture more of the water in that reinforced zone and direct it out through the face of the wall. The toe drain does a great job as well, but any reinforced mass like this, we recommend it, especially if you're going to have poor soils back there. Sometimes if you have a tall wall application such as these, it came up earlier as well, you might have multiple toe and heel drains which are at different levels, because if you're in a water application with a taller wall and you have, say, a flood event, it might be well above that lower toe and heel drain. So sometimes there's even multiple, but yes, that's to convey water from the reinforced zone. Any other questions? Well, I'm not seeing any other ones. So again, guys, I'm going to be sending out a follow-up email, which will include that evaluation form. It will include links to the next month's presentation. And if you guys have any questions, again, you can respond to that. I got a question. What about the software? Can this be made available? If you're talking about AB walls, yes. If Bill, if you don't have AB walls and you're interested in that, just respond to my email and I'll send you a link to download that. Otherwise, if you guys are listening now and you want to get the software today, I may be even able to send it out this afternoon. Just email me logan@allenblock.com. That's LOGAN. Otherwise, you can always email engineering@allenblock.com, And that's actually controlled by Laura Horseman, who's giving that next presentation, and we'll make sure to get you that software as soon as possible. All right, looks like that's probably it. So thanks so much, guys, for coming out, and make sure to keep an eye out for the future events. Have a good day.